Hey guys, my name is Kylie, and this section is going to focus on chemical bonding and some of the topics related to it. So these are things like Lewis structures, formal charges, and resonance. And so I'm going to be doing some of those, and then Bradley is your other academic mentor, and he's going to be doing the other sections. Okay, so to start off, we're going to talk about the different types of chemical bonds. And so just a note for this slide, anytime you see the abbreviation EN, that stands for electronegativity. So that's just a little helpful tip as we go through things. Okay, so out of all the chemical bonds that make up compounds, it can be divided into two major categories. So we have ionic and covalent. And then you can see here that covalent can get further subdivided into two more categories, which we'll talk about later. So we'll start with ionic bonds, which are formed between elements that have a large difference in electronegativity. So if you want a number value for that, it would be like a difference of greater than 1.9. But usually in your questions, you won't be given the actual numbers. And it's just kind of helpful to know that it's going to be a bond between an atom with low electronegativity and an atom with high electronegativity. So then it might also be helpful to know some examples of those types of atoms. So our low electronegativity atoms are typically like your metals in group 1 and 2. So that's on the left side of the periodic table. And then your high electronegativity atoms are things like oxygen or your halogens, so chlorine, fluorine, things on the right side of the periodic table. Another key thing to know about ionic bonds are that they involve a complete transfer of electrons. And so you can see in my example here, which is NaCl, so there is a ionic bond between these. And so the one electron that's usually around sodium has been transferred to chlorine. So now chlorine has 8 electrons around it instead of its usual 7. And then I also included this picture here because it's good for visualization purposes, just to understand that compounds that have ionic bonds form this type of lattice structure, and so it's very rigid and strong structure. Okay, so now moving on to covalent bonds. The key differences from ionic are that we have smaller differences in electronegativity, and also instead of a transfer of electrons, we have a sharing of electrons between the two atoms. Now, the details on this sharing is what gives us our two subcategories, which are polar covalent bonds and nonpolar covalent bonds. So with polar bonds, we have an uneven sharing of electrons between the two atoms. And with nonpolar bonds, we have an even sharing of electrons. So basically, those electrons are perfectly evenly distributed between the two atoms. And so you can see that in this picture here. It's kind of, this is a nonpolar covalent bond, and so that's why the color is kind of even all the way throughout. Whereas you can see in this polar covalent bond, we have electrons being more concentrated towards one side. And so again, this sharing idea comes down to the electronegativity of the two atoms. So remember, overall with covalent, our differences in electronegativity are already not as big as with ionic bonds. However, if there's still kind of like a difference, like an intermediate difference, then that's where we get our polar covalent bond. And then if we have a very, very small difference or even no difference at all, which would be the case if we have a bond between two of the same atom, because then they have the same electronegativity, that's when we get the nonpolar bond. And so just a note is that you can see that I included the actual numbers for the difference in electronegativity for all three categories. But like I said before, your questions won't usually ask you about specific numbers. And it's more important just to be able to identify like what the electronegativities of the two atoms are, and then what, like how big the difference will be between them. Okay, so now moving on to a practice problem. Part A says, which one of the following has the most polar covalent bond? So looking back here, we want polar covalent bonds. So the two categories that we're trying to eliminate are ionic bonds and nonpolar covalent bonds. And so immediately I can eliminate B and C, and that's because I can see that they're ionic. So looking at B, which is NaCl, we can see that we have an atom on the left side of the periodic table and then one on the far right. So that's going to lead to a big difference in electronegativity. And we have the same thing with RBF. So we have one atom all the way down here on the left and one all the way over here on the right. So these big differences in electronegativity we know are going to give us ionic bonds. And so I'm just going to write down there that these are ionic. And then we also know that we can eliminate D and E because these are a bond between two of the same atoms. So they're going to have no difference in electronegativity at all, and that's going to give us a nonpolar covalent bond. So then that leads us to saying that our answer for question A is answer A. And just to kind of verify that that makes sense, our bond would be between C and O. So we can see that those aren't two of the same atoms, so there will be a little bit of a difference in electronegativity. So it's not going to be nonpolar, but they're still close enough to each other on the periodic table that it's not going to be a huge difference that makes it ionic. So it makes sense that that would be a polar covalent bond. Okay, and then for part B, it says, which one of the following has the highest melting point? So anytime you see a question that's asking about high melting point, immediately you want to think ionic compounds. And the reason for that is if you go back to this picture of the lattice that I put, remember I said that that's a very strong compound. So or a very strong structure, sorry. So it's going to take a lot of energy to break that apart to become a liquid or to melt it. So if we're thinking about ionic compounds, then we know that we're basically going to be focusing on B and C. So we can eliminate those other options. And then when deciding between B and C, now is when we want to use our periodic trend in atomic radius. So R, B, and F are going to be quite different in size because we can see that one is all the way down here in row 5, whereas F is up here, it's going to be a lot smaller. In comparison, Na and Cl are very similar in size because they're both in row 3. And so what does that mean for our lattice? So when they're more similar in size, like NaCl, it's going to form a lot tighter and more compact of a lattice because they just fit better together. Whereas with something like R, B, and F, which are quite different in size, it's not going to fit as nicely together. So since NaCl is more compact and fits better together, that's going to have the higher melting point because it's going to take a lot more energy to break that compact structure apart. So our answer for part B is B. And that question, don't worry if it kind of seems a little bit complicated right now. It's a bit more of a challenging question because it requires you to integrate knowledge from like other sections, so like periodic trends. So again, don't worry if that one seemed kind of complicated right now. If you haven't gotten through all of your review, I just wanted to give an example of a question that's maybe a little bit more integrated that you might get. All right, so our next section is on Lewis structures. And so these are a way that we can use to represent compounds with covalent bonds. And so what I'm going to do is just go through the general steps of how to draw Lewis structures, and at the same time, I'll kind of use this example of NCO negative to illustrate those steps. So if you have to draw a Lewis structure, the first thing that you're going to want to do is add up your total number of valence electrons. So basically, you're going to want to go through each atom in the compound, see how many electrons it's going to contribute, and then add all of that up. So in this example here, nitrogen is in group 15, so it has 5 valence electrons. Carbon's in group 14, so it has 4 electrons. Oxygen's in group 16, so it has 6 valence electrons. So adding all those up, we have 15. And then if you do have a compound that is charged, then you need to account for that in your number of electrons. So a negative charge adds electrons and a positive charge subtracts electrons. So in this case, we have a charge of -1. So we are going to add 1 electron to our 15. In total, we have 16. And so if you had something that had a +2 charge, for example, then because it's positive, you're going to subtract electrons. And since it's 2, you would subtract 2 electrons from whatever that number is that you calculated. All right, so now you want to kind of start making the framework of your Lewis structure and just connect your atoms with single bonds. Now, sometimes it can be tough to know, which atoms are connected. So I honestly would just say kind of use your best intuition of what you kind of think looks right. As a tip, usually the atom in the middle is going to be your least electronegative atom. Or it's often carbon. So like, for example, that's the case for this compound. So one hint is that carbon's usually in the middle, so you could use that. Also, oxygen and nitrogen are more electronegative than carbon, so you know that those would probably go not in the middle and would probably be more towards the outside. Okay, so once you've done that, you are going to subtract the number of electrons that you kind of have used up now that you've put them in bonds. So every bond is 2 electrons. So here we made 2 bonds. So overall that's 4 electrons. We had 16 total minus those 4 that were in our bonds, leaves us with 12 electrons still to work with. So then our next task would be to take those 12 remaining electrons and distribute them around the atoms in the compound. But we don't want to just do that randomly. Our goal when we're distributing the electrons is to make sure that every atom has what we call a full octet. So what this means is that it has 8 electrons surrounding it. Now there are some exceptions to this. So hydrogen and helium only need to have 2 electrons around them. Boron specifically can have less than 8 electrons. And then elements in row 3 and higher, so by that I mean like row 3, 4, 5, 6, etc., can have more than 8 electrons around them. And so if we look at our example here, we don't have any hydrogen, we don't have any helium, and we don't have any boron. And N, C, and O are all in row 2. So we don't have any exceptions, and everything should have 8 electrons around it. Also, sometimes it's not possible to follow these octet rules without putting some of our electrons into double and triple bonds. So you can also do that in this step if it applies to that situation. Now you'll see with the 3 different options that I've put here, if you actually went through all of the atoms in these options, you'll see that everything does have a full octet. So we're all good there. But then how would we decide which one is actually the correct one? And that's where our 5th check step comes in. And so that's going to help us pick our best or most correct structure. So the first thing that we want to do is check our formal charges and see if they add up to the overall charge of the species. So you can see here I've already calculated the formal charges in blue, and our species has a -1 charge, so overall all of our formal charges should add up to -1. So you can see that's the case here, that's the case here, and -2 plus 1 also gives us -1, so that's good. So everything is good with this check, but then our second check is, do you have the best Lewis structure? And the best Lewis structure is the one where 1, our formal charges are minimized, and 2, they're consistent with electronegativity. And so I'll go through what each of those means. So an example of a structure where the formal charges are not minimized is this one here. So you can see that it is possible to draw a structure where we just have one charge, which is a -1. But in this case, we kind of overcomplicated things. We've got a -2, we've got a +1. It's just too much. So this structure does not minimize formal charges, so it's not our best structure. And then when we say consistent with electronegativity, what we mean is that we want electronegative atoms to be the ones that have the negative formal charges on them. And so you can see this is an example of something that does not follow that, because nitrogen gets that -1 charge, but it's not the most electronegative atom here. Oxygen is. So this is our best structure because our formal charges are kept very simple, just 1, and it's also that 1 charge is on our most electronegative atom, which is oxygen. So that's all the steps for drawing Lewis structures. Now, keeping in mind that this is a multiple choice test, so you most likely won't be asked to actually draw a structure. It's more likely that you'll get a question that gives you a bunch of options for a Lewis structure and asks you which one is the correct or best one. And so for that, I kind of came up with this little checklist here of like 3 things that you are going to want to check are correct when deciding which is the best Lewis structure. So the first thing is you want to check that the structure has the correct number of valence electrons, so it's consistent with the number that you calculated here. You also want to check that everything has a full octet, or if it is one of the exceptions, that it follows those rules. And then finally, you want to do a check of those formal charges, so seeing if they're minimized and checking if they're consistent with electronegativity. So we already went through the examples with the formal charges, but I just want to give an example here of a structure that is wrong because of its number of valence electrons and its octet. So if we count the number of electrons we have here, we have 2, 4, 6, 8 in the bonds, and then 9, 10, 11, 12, 13, 14 in total. And remember, our number that we needed was 16, so this doesn't have the right number of valence electrons, so it's wrong for that reason. Also, if you look at oxygen, we have 2, 3, 4, 5, 6 electrons around it, so we have an incomplete octet, and so it's also wrong for that reason. Okay, so now we have one of these practice problems here where we're basically given a compound and we're asked to pick the correct Lewis structure. So remember that the 3 things from our checklist that we kind of want to go through are number of valence electrons, checking for octets, and formal charges. So starting with number of valence electrons, we can add that up. So remember, carbon was in group 14, so it has 4 valence electrons. And then hydrogen has 1 valence electron. So if we have 3 hydrogens like here, that's going to contribute 3. And then oxygen and sulfur are both in group 16, so they both have 6. So if you add that up, overall we have 40 valence electrons. Now, for the sake of time, I've already added them up for all of these different options here. So A has 38, B has 40, C has 42, D has 42, and E has 40. And so if you want a reminder of how to add those up, basically how I always do it is that I always count each bond as 2. So I just go through it like 2, 4, 6, 8, 10, 12, 14, 16, 18, etc. And then for the lone pairs, I just add those. So for example, here I ended at 34 once I counted all the bonds. And then with these guys here, I just counted 35, 36, 37, 38. So I did that for all of them. These are the numbers that I got. So already this helps me eliminate A, C, and D. So now when I'm deciding between B and E, I'm going to next try and look at octets. And this will get better the more kind of structures that you look at. So I've seen lots of these types of structures. So immediately something that jumped out to me was this carbon here, because it seems to have a lot going on around it. And then if I look, so I'm just going to circle it here, I actually have 2, 4, 6, 8, 10 electrons around it, which is more than our octet. Remember, carbon is not one of these exceptions here because it's not hydrogen, helium, or boron, and it's only in row 2. So it should always have 8 and no more. So that violates that rule. And so that means that E is our correct answer. So looking at it, we have 40 electrons. That was right. And then that carbon, we have our issue is fixed because we have 2, 4, 6, 8 electrons, which is what we want. And so we didn't even end up having to go through formal charges. But I mean, if you did, this is a neutral compound, so we shouldn't have any formal charges. And again, because I've seen lots of these structures, I can already tell that there would be no formal charges here. But if you had extra time and you wanted to go through it, you would see that everything is 0, so everything's minimized and adds up to our overall formal charge of 0. So we know that E is the correct answer.
In this part of the video, we're going to look at formal charges and how you can assign formal charges to compounds. This can be really useful when it comes time to drawing Lewis structures and determining which Lewis structure best represents the actual molecule. A few things just in terms of rules. The formal charge on each atom in a molecule must equal the overall charge in the molecule. We will look at a few examples of where this actually applies. And the negative charge should be associated with the more electronegative atom. We know from periodic trends that our electronegativity increases from left to right and down to up in the periodic table. And the negative charge should be associated with the more electronegative atom because it more wants the electrons. I've also included the general formula for how to calculate formal charges. Now, that being said, I will also show another method that I would consider a shortcut to calculating formal charge associated with any atom. So really understanding how formal charges work, I think, is best illustrated through a few examples. So I've prepared a few examples to show using the equation that I have listed here, as well as the shortcut method. In terms of using this equation, we're going to first calculate the charge associated with the two oxygens that I've labeled with an orange, which contribute to these two. So we know that oxygen, for instance, has a total of 6 valence electrons, meaning the formal charge is going to equal the number of valence electrons, which is 6, minus the non-bonding electrons, which really this means just lone pairs. And these contribute to these here. So we have 4 lone pairs minus 1/2 our bonding electrons, which each bond makes up 2 electrons. So if we have 2 bonds, that means 4 electrons total, meaning then the formal charge associated with our uh, oxygens are 0. That takes into account this one and this one. In terms of our oxygens labeled blue, we already see that there is, just based on this picture, negative charges associated with these. However, if we weren't actually given this, we could calculate it based on the same approach using the equation. Formal charge is equal to, it's again 6 because oxygen has 6 valence electrons, minus the number of non-bonding electrons, which you see there is 1, 2, 3, 4, 5, 6, as well as then minus half bonding electrons. We see that atom is connected to sulfur through 1 bond, which means this contributes 2 electrons, meaning then the formal charge of our blue oxygens is then -1. In terms of sulfur, when we look on the periodic table, it also has 6 valence electrons, just like oxygen. So we know that the formal charge then, again, amount of valence electrons minus the amount of lone pairs it has, because sulfur does not have any lone pairs in it, has it's just filled with bonds. There's 0 lone pairs, and then we go to -1/2 our bonding electrons. We have 1, 2, 3, 4, 5, 6 bonds, which means 12 electrons. We then have a formal charge equal to 0 for our sulfur. Now, that's more a mathematical approach to it. We can now look at more the shortcut. This is the way I prefer. It's both time efficient and it's more a visual approach. So those who might not mathematically understand it, this could be perhaps a better alternative. So the first thing to really do is identify the atom as we had done previously, determining, for instance, an oxygen, sulfur, etc. Then we're going to want to treat all bonds. This is our pi and sigma bonds and valence electrons as single entities. And I'll show you what that means in a second. And you're going to subtract this by the number of valence electrons. And whatever that difference then is going to represent your formal charge. That's a mouthful. I think we should describe this via an example. So I've shown the depiction here. However, I will walk through it step by step. So if we were to draw just the Lewis structure of this, including our lone pairs, I'm not going to draw the formal charges right now, but we know then this is the best representation. So using that same approach, let's start at the very top, at this oxygen. We know oxygen has 6 valence electrons. So you want to, when you're calculating these formal charges, you want to actually start counting one less than the number of valence electrons. So for instance, oxygen, we're going to start crossing off our lone pairs and our sigma and pi bonds starting at 5. So I'll take this one slowly just to show you. So oxygen is 6, 5, 4, 3, 2, 1, 0. That means this oxygen, its formal charge is equal to 0, much like what we see here. In terms of the other oxygen, we can apply the same thing. It's 6, so we go 5, 4, 3, 2, 1, 0. Its formal charge is thus 0 as well. Now, we then look at the other atoms. We know that we can look at, I'll change color just to make it easier seen. We know this oxygen here is also 6, so we're going to apply the same rules starting at counting from 5. 5, 4, 3, 2, 1, 0, minus 1. So we know this charge, formal charge, is minus 1, like we see here. Applying the same to our other oxygen. 5, 4, 3, 2, 1, 0, minus 1. And last but not least, sulfur. If we apply the same, we know it also has a valence electron count of 6. 5, 4, 3, 2, 1, 0. It has a formal charge of 0. Alrighty, this is a good type of exam problem. It's asking uh, the formal charge of each of the atoms in the compound, and it's telling us that all hydrogens and lone pairs are shown. So you can approach this however you would like. If you would like to approach it using the equation or the shortcut I've shown you, I will approach it from the shortcut method. However, feel free to use the other method if you prefer that. So how I'd approach this situation in question is I see it's telling me that all hydrogens in lone pairs are shown, which means then that um, we don't have to draw in any more hydrogens that are might not be implied or any lone pairs that we would think might need to be shown. They're all shown. So off the start, uh, we have options A through E. I'm going to start on the left here with uh, this carbon. And so with this, we know carbon has 4 valence electrons, meaning if we apply the shortcut, it should be 3, 2, 1, meaning the formal charge of carbon is plus 1. From here, we can then rule out 2 options already. We know that carbon doesn't have a minus 1 charge, and we know it doesn't have a neutral charge. So it's either going to be A, C, or E. Now, looking at the next one, if we do oxygen, we know oxygen has 6 valence electrons. So 5, 4, 3, 2, 1, 0. Its formal charge is 0. We can look at our options. We see that both of these still have oxygen as a formal charge 0. So we are going to have to look at our nitrogen for its formal charge. We know that nitrogen has 5 valence electrons, meaning we start counting from 4. 4, 3, 2, 1, 0. Meaning nitrogen has a formal charge equal to 0. Meaning it can't be A, and it can't be C, meaning our best answer here is E. The next topic we're going to look at is resonance structures. These definitely take a lot of practice, and I would say off the start, it is helpful to use arrow pushing. And this just allows you to kind of illustrate where the movement of electrons will go. I find it personally, as a visual learner, helps a lot with being able to see um, how the movement of electrons causes resonance structures, because in resonance structures, it's not actually the atoms that are moving, it's just either the lone pairs and or the location of the pi bond. And as we've talked about in other topics such as Lewis, atoms that obey the octet rule must also obey the octet rule when doing resonance structures. Um, and also, just as kind of a lookout off the beginning, when you're trying to find which kind of compounds do have resonance structures, you want to see uh, if the compound, for instance, does have a double bond, or in other words, a pi bond, we can call that. So on the right here, I do show uh, a series of resonance structures. So we can see that the movement of uh, the lone pair of electrons can go into the pi orbital. However, in terms of that, if we input two electrons, that means that we also then need to output two electrons, meaning we can either have an output of two electrons here, or we could also have an output of two electrons there, which would give rise to then two different resonance structures. So on the right, I've shown uh, the movement of these electrons, giving rise to uh, this resonance structure. Of course, we can also then have movement of electrons here, causing alternative resonance structures, which I've just labeled uh, with, etc. Now, resonance structures, I think, are best identified with practice. So when we look at this question, it says how many of them have resonance structures? So off the start, we know that resonance structures, the approach that I would take is we know that it's the movement of electrons, and we know uh, it depends on delocalization, and that's just really another word of movement of electrons, and also involves pi bonds. So with that criteria, if we were to look at compound 3, for instance, it does not contain any pi bonds, meaning it can no longer, or it doesn't have a resonance structure, meaning right away we know that E cannot be an answer. Okay, so looking at the first compound, we see that it does contain pi bonds, and that is one criteria required for resonance structures. So if we were to treat these pi bonds as a pair of as a lone pair, we actually can have delocalization about the pi bond, causing a resonance structure as follows, which would give rise to, sorry, a resonance structure as such. And now, one thing I did I meant to mention in the previous video was that overall this compound is neutral, meaning it should have all the charges in the molecule combine to be, or its resonance structure should have all the charges sum up to what the compound is initially. So in this case, we see our starting compound is neutral, and a resonance structure of that has both a cation and an anion, meaning that it also remains neutral. So we know that at least one of them so far does have a resonance structure, which rules out option A. In terms of our second compound, we see that we have an anionic compound because we have uh, a carbon with a negative charge. This lone pair can be delocalized because of the adjacent pi bond illustrated here, meaning we could have delocalization of our electrons, causing uh, the following resonance structure. And again, we can assign then a formal charge to our oxygen, which overall still results in a negatively charged compound. And as a recap, we could assign that formal charge by either using the formal charge equation or that shortcut I showed, where we take the number of valence electrons and start counting backwards, uh, treating our lone pairs and our bonds as one individual. So as a recap, I can show this here. We know that oxygen has 6 valence electrons, meaning we'll start counting from 5. 5, 4, 3, 2, 1, 0, -1. Hence our formal charge is equal to -1. So we know that then we have 2 that have resonance structures, meaning B is not an option. And we already had determined that our third compound does not have resonance because it cannot have delocalization uh, or movement of electrons. So we either then are left with options C and D. And as for our last compound here, we see that we have an anionic species where we could also have delocalization of our electrons, meaning that our fourth compound does in fact have a resonance structure as follows. And again, we can then assign our formal charge if you would like for extra practice. And we can see really what resonance structure comes down to is just the delocalization of electron density. We see that we have a negatively charged oxygen species on the right side, and then a resonance structure of that causes the delocalization of that charge to then be associated with a new oxygen species as follows. So we can confirm that this compound then does also have a resonance structure, meaning C cannot be an answer, and our best representation would be option D.